In traditional classrooms, speed is the ultimate proxy for intelligence. Finishing the test first is how we define the smartest person in the room. Yet, students who excel at these exams often lose the material entirely within a few weeks of the final bell. This rapid forgetting follows a predictable biological pattern based on the test's own design. Demanding exact, rapid factual recall limits the brain to its most fragile, algorithm-based memory circuits. By optimizing for speed and single correct answers, standard assessments actively bypass the biological centers of higher-order thought. Complex, uniquely human thought relies on the prefrontal cortex, the hub for integration and executive control. During a standard associative recall test, activity is isolated and brief, completely bypassing the frontal lobes. But an open-ended conceptual problem triggers a complex cascade of connections, bridging the temporal and parietal lobes, routing heavily through a glowing prefrontal cortex. To measure true higher-order learning, assessments must move away from single-answer formats and toward tasks that trigger this adaptive neural integration. Higher-order learning is a physical, measurable neurological event. Traditional tests record the wrong physiological process. The brain records specific time and space-dependent events and rote details in the episodic memory system. Because these memories are context-dependent, the node decays into static if the information is not consolidated. Semantic memory, by contrast, stores abstract, generalized concepts that remain stable regardless of the original context. Through sleep and protein synthesis, episodic traces physically transform into durable semantic knowledge. Standard academic exams overwhelmingly target the fragile episodic system through associative recall questions. These tests provide precise data in the immediate short term, but they generate inflated estimates of actual, lasting knowledge. Testing specific episodic details leads to rapid forgetting, while assessing generalized semantic concepts targets information with biological durability. The brain uses two different decision-making models to navigate the world. Veridical decision-making is the process of finding one intrinsically correct answer through predictable algorithmic steps. Conventional computers excel at this type of exact sequence processing, moving predictably from input to a binary output. Adaptive decision-making is required for ambiguous, real-world situations that lack an inherently correct solution. The prefrontal cortex handles these situations by evaluating competing variables like context, logic, and history simultaneously to find an optimal choice. Computers own the veridical domain, but the human prefrontal cortex evolved specifically for this type of adaptive, flexible reasoning. When we design tests around single correct answers, we treat the human brain like an inferior calculator, ignoring its primary evolutionary advantage. Educators often assume that a fast, effortless response indicates deep subject mastery. Neurobiology calls this automaticity, the fading of conscious access to a skill as it becomes a habit. There is an inverse relationship between rote practice and high-level brain engagement. As repetition increases, cortical activity plummets. Routine, highly practiced tasks require significantly less brain power. An instant answer on a test often signals that the student has lost executive control over the task, relying instead on unconscious habit. Effortless speed proves a reduction in higher-order cortical engagement, which invalidates the test as a measure of deep intelligence. The prefrontal cortex must physically bridge highly specialized, distinct regions of the brain. Roger Sperry won the Nobel Prize for proving the brain relies on physically separated, unique processing centers. These distinct regions perform different, non-interchangeable functions. Routing data from highly specialized regions through the prefrontal cortex is a physical process. It takes measurable biological time to complete this integration. This slow, deliberate integration is incompatible with the hurried time constraints of a standardized exam. A strict deadline acts as a physiological filter. It excludes the slower prefrontal pathways and forces the brain to rely on the isolated, unintegrated networks of rote memory. The stopwatch is not a measure of rigor. It is a physiological barrier that prevents the brain from performing complex synthesis. A successful assessment must move beyond simple data retrieval to trigger a specific biological state. Giulio Tononi's integrated information theory provides the framework for measuring this high-level cognition. High-level thought is defined by neural complexity, which requires a vast amount of differentiated information scattered across the brain. For complexity to emerge, these disparate clusters must be integrated into a single, unified web. This high neural complexity is the biological signature of wisdom, the ability to apply abstract concepts across disciplinary boundaries. The goal of learning is the physical, structural evolution of the brain towards this state of higher complexity. We can translate these biological requirements into a practical strategy for assessment. First, we must eliminate strict time limits to accommodate the physical reality of cross-network prefrontal integration. Second, questions must be open-ended and ambiguous to force the brain out of algorithmic habit and into adaptive decision-making. Third, we must test for abstract conceptualization rather than the exact regurgitation of rote details. This framework shifts the brain's architecture toward lasting, integrated knowledge. Aligning test design with neurobiology ensures that the assessment process itself triggers the integrated neural activity required for higher human consciousness.